So the chain rule, now that we have it, is actually going to allow us to do a complete proof of the power rule. We established the power rule previously, we'd said we demonstrated it using positive integer powers, and then the proof of that came from the binomial expansion theorem. For negative integer powers, with some slight adjustments, we were able to do the same thing. But beyond that, the only other non-integer power we were able to prove it for was x to the 1/2, or the square root of x. And we got through that using the limit definition of derivative and multiplying by the conjugate, which is great for a difference of squares, for square root, because the difference of squares cancels out the square root, but it's not going to work so well for a third root or a fourth root or a fifth root. So we need to be a little bit more general here. And that requires an interesting little technique. So first of all, this is the power rule. The derivative with respect to x of x to the n is equal to n times x to the n minus 1. So for all intents and purposes, the power becomes the coefficient, and we subtract 1 from the power. And this is effective for all powers out there except for 0, which, as it turns out, doesn't matter because x to the 0 is simply the constant 1. And the derivative of a constant is 0. So for that particular value, the power rule doesn't exactly apply, but that's okay. Now, that being said, we would like to be able to show that this is true for any real number power n. Rational, irrational, fraction, decimal, whole number, positive, negative, anything except for 0. And the trick is going to come in a very careful and very particular way of rewriting x to the n. Now, we can, and this is something that we've been doing most of the semester now, and we'll continue to do so, when an expression is written in a form that is not particularly helpful or that doesn't do what we need it to do, there's always an equivalent form out there. And the typical way that we write an equivalent form is to simplify in some way, to expand a power of a binomial, to factor, to divide out a common factor from the numerator and denominator of a fraction, for example. But there's another way. We can introduce new operations, so long as we then balance it out by introducing the inverse operation immediately thereafter. We saw this in the proof of the product rule. In this case, it's a simpler but more elegant combination of things. I'm going to suggest that we can take x to the n and perform a logarithm on it. So we introduce this new operation. It needs to be immediately followed by the very next operation has to be the inverse of this. And the inverse of a natural log is exponentiation base e. And this is going to be the trick to it, that we can replace x to the n in that derivative with this. So that's going to be the key for how we get through this. And the chain rule is necessary because what we've done is we've created a composition. We have x to the n inside of the natural log, and then the natural log of x to the n is inside of e to the power, the exponentiation base e. So the chain rule is necessary to do this proof. So let's take a look at it. Instead of the derivative of x to the n, we're going to use the equivalent form e to the ln of x to the n. Now, I did mention that e to the ln of x to the n is actually one function inside of a second, inside of a third. And that's kind of messy, and it can get a little bit disgusting, but logarithms have a way around that. There is a property of logarithms that says if we're doing the logarithm of an expression that has an exponent, that exponent can come down in front of the logarithm. And that breaks the nested composition there because n is a constant. So instead of a composition, we one function side of a second side of a third, we now have a product, which is much simpler, inside of the exponentiation. So that's going to be our inside function, the n times the ln of x. So let's apply the chain rule. Let u equal n times the natural log of x. So that the derivative of our expression there becomes the derivative with respect to x of e to the u. So we need the derivative of the inside function. That's our du dx. Now, the thing to remember here, the tricky part, is that n is a constant. It's an unspecified constant, but in any problem, like if this was the derivative of x squared, n would be 2. So in any particular problem, n is a constant. So as a constant multiplier, it carries straight through to the derivative. The derivative of the natural log of x then is 1 over x. Now this is almost an airtight proof because there's only one part of this that we haven't proven per se yet, and that's that the derivative of the natural log of x is 1 over x. So it's not an airtight proof just yet, but we certainly are going to see that if we allow that to be true without having proven it, that we'll be able to see the power rule working for any power n. So we've got the derivative of u with respect to x, and now we need the derivative of e to the u with respect to x. Well, the derivative of e to any power is e to that power. So, putting it back together, the derivative of e to the n times ln of x is equal to the derivative with respect to u times du dx. And from here, we can resubstitute to get it back in terms of the original variable. U is n times ln x, and du dx is, well, we can clean that up slightly and make it n over x. Now, that doesn't exactly look like the power rule just yet, but if I might suggest, this wasn't the original form of the function either. The original form was x to the n. We did a couple of little things to change that. So going backwards, we can take this e to the n times ln of x and rewrite it as its equivalent form, its original form, x to the n. Well, we have our times n. What we just need to do is simplify this. But this is covered by a property of exponents. If we have the same base, or two expressions being divided with the same base, we can subtract their exponents. So, n minus 1. And there we are. Without ever actually needing to know what the value of n is, because at no point was it actually involved in any of the work that we did. Without needing to know what the value of n is, we were able to show that the derivative of x to the n is n times x to the n minus 1. Now, part of the reason this only works, or this doesn't work when when n equals 0, is this right here. If n is 0, then this is, the whole thing boils down to a constant. This becomes 0, and the derivative of 0 is 0. So we have a times 0, and that wipes the whole thing out. So it doesn't really apply in that case. Now, technically speaking, if you're careful enough, the coefficient will take care of it and make sure that you get the right answer at the end, but we're just going to take it with a grain of salt, that n not equal to 0 thing. Because we don't want to accidentally, start taking x to the 0 and subtracting 1, getting x to the negative 1. That's not correct. So, that being said, without needing to know the value of n, which means n could be anything. Positive, negative, fraction, decimal, whole number, rational, irrational, anything. So, the chain rule, in conjunction with this clever introduction of inverse operations, allows us to finally at last verify that the power rule does work for any real number power of n, of x. And again, there is only one minor little snafu that we haven't actually proven yet, and that's that the derivative of the natural log of x is 1 over x. We simply established that as fact and said that explanation will come later. And sure enough, in a couple lessons we'll get there. But for now, we'll take that as a fact. So there we have it, the power rule for any real number power of x.